Now we get to do oscillations. Whoa. Let's see. So now we go into the next topic, which is actually good review for the exam. So, you know, there's that. Yay! Although we won't get to the good review part. Oh. Okay. This needs to go away. All right. Now just start here. Okay, with this next topic, we're inching our way towards like waves and light and all that sort of more fun stuff. Okay, so this next section is the chapter is called Oscillations. Okay, we're just going to do fun stuff now because there's only 15 minutes. We're going to do it fun. So oscillations, you know what that is: repetitive, back and forth motion. It could be a lot of things can oscillate. Anything vibrating is oscillating. Anything moving in a circle is technically oscillating. A mass on a spring is oscillating. Right? So this is our baby's first simple harmonic motion is always, oscillator is always mass on a spring. Yes. If you decide to be a physics major, I'm going to get one of you. You're going to spend like a year on that. Oh, wow. Okay, not a year. You'll use two of them, and then it'll be a year. So let's start. Our first oscillator is start with simple harmonic motion, which is usually abbreviated S. I like to abbreviate SHN, and it's not M. It's not simple. Okay, nothing is simple. But simple just means it's moving at one frequency, basically. Harmonic means frequency, simple means one of them, and motion means it's moving. So we actually did this already. We were talking a little bit about describing motion at fundamental level. We sort of already did this. We said, oh, if you have a mass M on a spring K, and its natural length is that the origin O, how's it going to move? And we said, oh, okay, well, how anything moves, it's Newton's second law. So you say sum of the forces minus kx, if we're just doing the x direction, equals ma. But just to move quick, we'll say ma is a second derivative of position with respect to time. Oh, yeah. Right. And remember, as like, what function can you think of that's equal to its own second derivative? And the answer was that you guess. Remember that whole fun thing we did? Nobody came down, one person. Yeah. So to solve this, you guess. Differential equations, that's what's happening in that class, 103 or 4, whatever it's called here. Okay. You guess, but now we're going to get a little more sophisticated. So last time we guessed, but, you know, we just said sine. Okay, let's guess with a little bit more purposefulness. All right. We're going to guess. We're going to guess sine. I heard somebody whisper it. I don't want to disappoint you, so yes. We're going to guess. We're going to construct our solution, as the mathematicians say. So yeah, sine. Okay, here. Are we done? No. Let's draw a sine. Let's see. And let's think, does the thing really move like a sine? Yeah. You know, you can see it moving up and down here. It's kind of like a sine, if you know what a sine looks like. If you can imagine a sine. The sine of 0 is 0. So we could draw a sine real quick. Like that. So that is sine, but this is like the math world. We need the real world, right? So we want to guess, did that fall off? Did everybody have their protective eyewear on? No, okay. So solution needs parameters to make it like a physical expression, right? Things have units. We can't just write sine. Okay, so let's think one parameter is as this thing was moving up and down. The highest it goes is we call the amplitude of the sine wave, and the lowest we go is minus a, right? So if you have a sine wave, you know that it goes from some value maximum to some value minimum. And you know in a sine from math where that goes. It goes right there, right? Because sine goes from 1 to 0, so if you multiply by a, it goes from positive a to minus a, right? So when we make our guess, we would probably put an A there, Right? And then you'd say, okay, sine, and just put a t here. It's like, no, you can't just put a t there. Let's go ahead and put the t there. Right? It's a function of time, but you can't actually take a sine of something with a physical unit. Okay? You can't take a sine of something with time. You can't take an exponent of something with time. You can't take a cosine of something with time. The only unit you're allowed to have in here is radians. Right? So you've got to have radians in there. So we have to convert that sine, or that t, to radians. So we should look back at our sine wave and think, is there some parameter that would allow us to do that? And that parameter is the period. It's how fast the sine wave happens. Right? So t is what you've heard of before, is the period. When we were talking about circular motion, these are all the same ideas. 1 period equals what in radians? 2 pi radians. Right? 1 period is 2 pi radians. So if we want to convert, what this thing really wants to know is how many radians has it gone through? Well, at a certain amount of time t, it's gone through 2 pi over t radians. Right? The time, the variable time over the period is how many cycles it's gone through, and one cycle is 2 pi. Okay? When you're doing circles, one circle is 2 pi. When you're doing cycles, one cycle is 2 pi. A cycle and a circle are the same thing. And depending on your accent, they are actually the same thing. And then we've got another thing here. So let's see. So inside the sine must be radians is sort of our justification for this. But then we need one more thing. Oh, this is the bad one. Oh, no. Is we have to have a phase plus phi naught. Right? It's just a phase. Don't freak out, okay? It's just phi naught. Everybody freaks out about what the phase means, okay? And here's the reason we have to have a phase is, let me set it back up. Somebody knocked it off. Right? When we set it back up, sine is at 0 at time equals 0, right? And we put it over here. So sine is at 0 at time equals 0, but does it have to be at 0 at time equals 0? Right? Time equals 0 could be now, or now. Or if you're really smart and know how a sine works, now. Right? So it doesn't have to be 0 at 0. Right? I didn't even label this as 0. You just thought it was 0. Actually, I meant to say, oh, down here is 0. Oh, right? So here's time equals 0. Okay? So all phase does is it shifts the curve left and right. Shifts the, I'll call it the curve, you know what I mean. Left and right, assuming you have time, on the x-axis. So it's just a little constant to help you decide where 0 is. Okay? If you're smart when you set up a problem, you pick sine or cosine correctly so you don't have to deal with a phase. But you're learning that. Okay? So this is the guess we would make right here. A sine 2 pi over period t plus phi naught. And then that has like all the free parameters you need. Okay?